Next talk is on optimal proximity gaps again, and Rohan will give us the talk.
Hi, thank you. So this is similar in spirit to what Swastik was just talking about. This is joint work with Venkat Guruswamy, and this is about optimal proximity gaps instead of up to just Johnson bound. So I'll again do the same codes 101 that will happen in every talk. So for me, I'll only talk about linear codes, again, just because as Swastik described, the problem makes only sense for linear codes, essentially. Distance will always be the Hamming distance, and there's one thing to note that I am always talking about distance as normalized. So my distance is always between 0 and 1. Rate of distance of the code is the standard thing. Rate of the code is as before. And I want you to think that rate plus distance is basically 1. So 1 minus distance is rate. Yeah, and that's how I want you to think about things. Yeah, so this is, we have seen before. Good. So I'll briefly tell you about the Fry protocol that Swastik alluded to. So this is a fast Reed-Solomon IOPP, active oracle proof of proximity. So what is the setup? I want to prove that a given oracle, some given oracle function, is either degree D or some amount or far from being degree D. So there's a prover and there's a verifier. The prover will break this function. This is the FFT stuff Swastik was talking about. You break the function f of x as f naught x square plus x f1 x square. Very simple. Now the verifier just sends a random value alpha, and the prover will now send you an oracle that g of x, which is f naught of x plus alpha f1 of x. So now you want to verify if this function is now degree over d over 2. And if you repeat, you can go down to constant degree, and then you can just hopefully verify. And you check if the oracle is consistent with the original function by querying on a few points that you can do. And now you've proved that this function is d over 2. Is this not d? This is d over 2 or far. So we started with f of x, which was this function, and we have reduced to such a function. The hope is that if either of them, if they're both low degree functions, then a random linear combination is a low degree function. But if either of them was far from being low degree, then the random linear combination should also be far from being low degree. So instead of checking each separately, now we only have to check a random linear combination, and we can recurse. So this is the whole basic setup, basic idea. And the question of proximity gaps is really, when is this a good idea? Up to what distance? What is the soundness error? Okay, so that was the Fry protocol. That is the motivation of asking about proximity gaps. I'll try to define some things formally. So we have something concrete. So this is correlated agreement. So I want to say if a random linear combination is close to the code, then there is a good geometric explanation for that in the code space. This is slightly different from how Swastik presented it. So if there's a line, which is this noisy line, which is close to the code, then I want to say within the code space, there is also a line which explains why this was close. So I'm saying that if there are many points with high probability over a random linear combination, of U0 and U1, it was close to the code. Then there's C0 and C1 in the code space, and this entire line is actually close to this noisy line. So it's some kind of geometric explanation for the closeness of this line. Okay, so the main question is what codes have proximity gaps up to capacity, or optimal proximity gaps up to 1 minus rate, and with good error bounds. And this is the Ethereum price question as well. For concrete Reed-Solomon codes, do you have proximity gaps up to capacity? Good. So what is the previous best known? It's from our the previous talk. So up to 1 minus square root r, this is the Johnson bound mentioned in the previous talk, we do have correlated agreement and proximity gaps for standard Reed-Solomon codes. And this was the best known for any family of codes before our work. And this, as Swastik told you, is really coming from running list decoding algorithms for Reed-Solomon codes, like the Guruswami-Sudan algorithm. And there is we don't really know even list decoding, and this seems like a more complicated object to understand. So it seems hard, at least, to go beyond Johnson bound and approach capacity here. And this work and Kreitzer basically said that in some way that you need to prove better list decoding first for Reed-Solomon codes if you want to uh, get optimal proximity gaps and solve this Ethereum price question. So good. So then the natural question to ask is, well, okay, Reed-Solomon is not the only code family we know. What codes have proximity gaps up to capacity? So can you go beyond Reed-Solomon? So we don't think you can do list decoding beyond for general Reed-Solomon. So what about other codes? So Guruswami Rudra in a breakthrough work in 2006 showed that there's this family of codes called the folded Reed-Solomon codes, which achieve list decoding capacity, i.e. are list decodable from just delta distance of the code minus epsilon errors. And Chen and Zhang showed in a recent breakthrough again that this folded Reed-Solomon, there's like a more general subspace design codes family, which gets like best possible list size actually. So like folded Reed-Solomon are not just like list decodable, they're as good as it gets. And in another work, Al-Rabia Guruswami Lee and Goran Zhang also showed that random Reed-Solomon and random linear codes. And okay, there's a missing citation. Bracken, Gopi, and Makam should also be mentioned here. But these codes are actually 1 minus R, also have optimal list decoding. So now the question is, what if you use these codes instead? Where we do node list decoding, can you get optimal proximity gaps? And that's what our work shows, that actually for all of these families of codes that I mentioned, you get optimal proximity gaps. So up to 1 minus rate minus epsilon, as good this the capacity, we get optimal proximity gaps, and we get it with the linear dependence and a very good dependence on epsilon as well. So this includes codes such as folded Reed-Solomon code, univariate multiplicity codes, random linear codes, explicit AEL-based, expander-based codes, random Reed-Solomon codes, and all of these families. Yeah, so this is the main result. And now I want to talk to you a little bit about techniques and what goes into proving such a result. So our main idea is like, okay, one thing we do is like we come up with a more different abstraction, which we call line decoding, which will imply some strengthening of correlated agreement that we have talked about, called mutual correlated agreement, which is something the practical cryptography people seem to care about, which will imply proximity gaps and correlated agreement and so on and so forth. So this is a much cleaner abstraction in our, to us. So what is this definition? Line decoding. It looks somewhat like correlated and mutual correlated agreement. So a code is delta comma a comma b line decodable if amongst any set of a code words which are close to the line, b are collinear. So let me show you a picture. There are these marked things which are close to these circle. Can I? Over here? No. Okay, I don't have a list. So these points are not code words, but like there's these noisy bigger points. So they are not along these are noisy line. You can see is the blue line, and then I'm saying that there are many close by code words, and amongst them they also form a line. Okay, so this is a different kind of explanation. So then list decoding is saying that there are not too many close by code words to an element. And now our line decoding definition is saying there are not too many close by non-collinear code words to an element, to a line. So it's some sort of degree 1 condition. And we handle higher degree conditions as well in our paper. So you can prove this delta over 3 and 1 minus, like this 1.5 Johnson bound that was being mentioned earlier in this abstraction as well. And that has happened. So this is the definition that actually makes a lot of things easier for us. So how do we list decode? So um, list decoding algorithms typically work in two steps. The first step I will say is finding a low dimensional space. So Gurusamy Wang showed that all code words close to a received word for multiplicity codes and Fourier-Solomon codes lie in a low dimensional affine space or low dimensional linear space. And this is usually easier that like if proving that 1 by epsilon close by code words is hard, that there are not more than 1 by epsilon close by code words, but it's often a lot easier to prove that there are no 1 by epsilon linearly independent code words which are close. Because these are linear codes, it becomes a lot easier to prove linear independent things about linear independent things. And the second, this is easy to show, you can think of like random linear codes. Because you don't have independence if you don't have code words that are not linearly independent. So it's harder to prove that they won't land close by. But if you considered 1 by epsilon linearly independent things and now sample, all of them landing close to a given word is unlikely. So this is usually easy. And the second step is a pruning step. So in a long line of work, you can see that they have shown that actually, once you give me a low dimensional space, I can show that inside any low dimensional space, there are very few things close to a code word. So there is a statement that you can prove of this sort for all linear codes. And that is by Kopati, Ronzevi, Seraf, and Wouters, and Tamo. And then there are strengthenings for these subspace design codes that have been referred to, like Fourier-Solomon and multiplicity and so on. So this says that somehow that list decoding bounds hold for low dimensional spaces. So we follow the same template. We follow Goswami Wang, and these are the two steps. So first step, we show that all code words close to a given line lie in a low dimensional space for these Fourier-Solomon, multiplicity, and so on. And the second, we show that line decodability in some sense holds for low dimensional spaces. So I want to say a few words, but I don't want to show you because this will get involved. The second step, Chen and Zhang have a very, like an optimal bound for showing this, that there's 1 by epsilon, many close by code words to any element. But there's also a very nice result by Srivastav, which showed 1 by epsilon square bound instead of 1 by epsilon, which is not optimal. But one nice thing about that algorithm which turned out for us is we were able to generalize it to these lines. So our result, in some sense, we don't know if it's exactly optimal up to the dependence on epsilon. Yeah, but we could use the Srivastav and Ashwin Kumar Habib's Srivastav algorithm here. So let me recap. What are our results? We show that almost all codes known to be list decodable up to capacity have proximity gaps and mutual correlated agreement. And this includes all these codes that I mentioned. So our results, the way I presented, actually hold for this broader class of codes called the subspace design codes. And as mentioned before, Gurusamy Kopati showed that Fourier-Solomon codes and univariate multiplicity codes are subspace designs. And we now know also how to construct, using expander-based codes, how to construct subspace designs. So due to these reasons, you can subspace design codes have this behavior. But now randomly linear codes, completely linear code, a random linear code can never be a subspace design, actually, in the way that I've said. So, but we prove results for them as well. So they are through this connection of like local LCL properties, local coordinate-wise linear properties that, yeah. So there's a result by Levy, Moshev, and Shagretea that show that random linear codes and random Reed-Solomon codes have exactly the same behavior in terms of local properties. And due to the work by Brakenzik, Chen, Dhar, and Zhang, we also know that this is the same behavior as subspace design codes. So using their techniques, we were able to import these results from subspace designs to random linear codes and random Reed-Solomon codes as well. And this actually also holds for random LDPC codes. So yeah, those are our main results. And I'll just quick summary slide that our the key role we have is like this really just this clean abstraction of line decoding. It makes a lot of the previous proofs look much cleaner. Um, and it's like implicitly there in many works, but it was never explicitly defined. There's another independent work by Havok which has this definition, but I think this abstraction really simplified a lot for us. Then the technique is really subspace designs plus list decoding methods. We use this pruning methods from Srivastava, and then we define some local properties to capture line decoding as well. Yeah. Thank you.
We have time for a quick question.
Or like, you said like you're inspired by the Srivastava work,
Mhm.
and and this also the Srivastava work is not so optimal. It's just one reference square.
Mhm.
Yeah. So I'm wondering like, what is your conjecture the like ideal optimal bound? Like, if in a word you can improve, if you can improve, you can improve the optimal bound. So which parameter would be improved?
Good. So here it won't really be an improvement. So the question I will phrase as the line decoding question. So we were able to combine line decoding plus list decoding in a very nice way, which if your goal is just correlated agreement of proximity gaps, you get good enough things. But the question is the following, that I want to say that if you give me so and so many points, which are close, code words, which are close to a line, then 3 of these code words must be collinear. Just 3 code words must be collinear. So Srivastava's work and AHS will give you order 1 over epsilon square. Many close by points are needed. The question is, can you just get away with order 1 over epsilon?
Okay, let's thank our speaker again.